Imagine standing before a bottomless abyss, but it is not a hole in the ground. It is a distortion in the very fabric of space and time. That is a black hole. A black hole is not a hole in the ordinary sense. It is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Beyond this point, every possible path leads inward toward the center, a place called the singularity, where density and space-time curvature approach infinity according to current equations. The concept of black holes arose from the theory of general relativity developed by Albert Einstein. In 1915, he proposed that gravity is not an invisible force pulling objects together, but the curvature of space-time caused by mass. When a massive star collapses under its own gravity, it can bend space-time so extremely that a black hole forms. Interestingly, Einstein himself once doubted whether such objects could truly exist. Yet the universe proved that his equations allowed for something far stranger than he imagined: the birth of cosmic monsters. A black hole forms when a star at least 20 times more massive than the sun runs out of nuclear fuel. Without the outward pressure from nuclear fusion to counteract gravity, the core collapses in an instant. This collapse produces a brilliant supernova explosion, but the remaining core becomes compressed beyond imagination. If massive enough, it bypasses all known states of matter, including neutron stars, and continues collapsing until a black hole is born. There are three main types of black holes: stellar black holes, formed from the death of massive stars; supermassive black holes, found at the centers of most galaxies, including the Milky Way; intermediate black holes, a less understood category between the two. At the center of our galaxy lies Sagittarius the Asterisk, a supermassive black hole around which stars orbit at incredible speeds, as if dancing around an invisible god. But what makes black holes truly mysterious is not only their gravity, it is the unanswered question of what lies within. The singularity, where physics breaks down. According to general relativity, at the heart of a black hole lies a singularity, a point of infinite density and infinite space-time curvature. But in physics, infinity often signals that our model is incomplete. Modern physics stands on two pillars: general relativity, describing gravity, and large-scale structure quantum mechanics, describing the subatomic world. The problem is that these two theories do not agree when applied to singularities. At the center of a black hole, both should apply, yet they contradict each other. This opens a bold possibility. Perhaps the interior of a black hole is not an end, but a door. The Einstein-Rosen bridge, a tunnel through space-time. In 1935, Albert Einstein and physicist Nathan Rosen discovered a special solution to Einstein's equations. They found that space-time could theoretically form a structure known as an Einstein-Rosen bridge, a tunnel connecting to separate regions of space-time. Today, we call this a wormhole. Imagine space as a flat sheet of paper. To travel from point A to point B on opposite ends, you must cross the entire surface. But if you fold the paper so that 2 points touch and punch a hole through them, you create a shortcut. A wormhole is that shortcut through space-time. If a black hole is an entrance, perhaps there exists an exit elsewhere, possibly a white hole, or even another universe entirely. White holes, the other side. In theory, if black holes allow matter only to enter, then the equations also permit the existence of objects that allow matter only to exit, called white holes. White holes have never been observed. Yet mathematically, they remain valid solutions. Some speculative ideas suggest white holes may be the opposite ends of wormholes. Our universe might have been born from a white hole in a parent universe. The Big Bang itself could have been a white hole eruption. These ideas push the boundary between physics and metaphysics. Hawking radiation. Black holes are not completely black. In the 1970s, theoretical physicist Stephen Hawking made a groundbreaking discovery. Black holes are not entirely black. According to quantum mechanics, particle-antiparticle pairs constantly appear and annihilate in empty space. If such a pair forms near the event horizon, one particle may fall into the black hole while the other escapes. The result is a faint emission known as Hawking radiation, meaning black holes gradually lose mass over time. If this theory is correct, black holes can eventually evaporate over unimaginable timescales. But this leads to a terrifying question. If a black hole disappears, what happens to the information about everything that fell into it? This is the famous black hole information paradox, one of the greatest unresolved mysteries in modern physics. A gateway to another universe? If wormholes exist and can be stabilized, they could connect distant regions within our universe, connect different points in time, or connect entirely separate universes. Some physicists suggest that microscopic wormholes may constantly form and vanish at quantum scales. Tiny fluctuations in space-time foam. If advanced civilizations could somehow enlarge and stabilize one, possibly using exotic matter with negative energy, still purely theoretical. It could allow instant interstellar travel, time travel, or passage into parallel universes. Black holes as universe generators. One radical hypothesis proposes that each black hole might create a new universe within it. According to this idea, instead of ending at a singularity, collapsing matter might bounce into another dimension. The new universe could have slightly different physical constants. Universes that produce more black holes would generate more offspring universes. This concept is sometimes referred to as cosmological natural selection. If true, our universe could exist inside a black hole from a larger universe, and the black holes in our universe may be pregnant with universes of their own. Can wormholes be traversed? The main problem is stability. Most models suggest natural wormholes would collapse too quickly for anything to pass through. To hold one open would require negative energy, something not known to exist in large quantities. Certain quantum effects, such as the Casimir effect, hint that negative energy might exist at microscopic scales. But turning that into a stable cosmic gateway is another matter entirely. For now, wormholes remain theoretical, but they are grounded in serious mathematics. From science to science fiction, the idea of wormholes and black holes as cosmic gateways has inspired countless works of science fiction. The film Interstellar portrayed the black hole gargantua using real physics calculations, astonishing audiences worldwide. Many elements in the film were developed with consultation from leading physicists. The line between science and imagination grows thinner each year. What truly lies beyond? We have never directly observed the interior of a black hole. Everything we know comes from mathematics, indirect observation, and theoretical modeling. It could be a true singularity, a bridge to somewhere else, or an entirely new quantum structure we have yet to understand. What is certain is this: black holes are not merely cosmic monsters. They are natural laboratories where the laws of physics are pushed to their ultimate limits. A door or a wall? Black holes might be the absolute end of matter, the beginning of a new universe, or the place where we must rewrite physics itself. The gateway hypothesis remains unproven. Yet it is not pure fantasy. It arises from the very equations that describe our universe. Perhaps the most astonishing fact is not that black holes exist, but that the universe allows tiny beings on a small blue planet to imagine that such doors might be real.